Hello, Chem 2. Welcome to this second video of the week. This one's going to revolve around two concepts, one more mathy than the other, but as you can tell by the little thing in the bottom, there's still going to be a sizable amount of math associated with this concept. So what are we going to do? Well, we've already taken care of initial rate data. We've already taken care of concentration time data. That's what we did in the video from yesterday. If you've already gotten ahead of yourself, I apologize. If you tried to watch the videos, both videos that I posted yesterday, you realize the second video, the one that I'm redoing now, actually had no sound. I have no idea why. I do now have an idea why, but hopefully that's not going to be the case and we're going to have this go off problem-free. So, administrative items, you guys have the OWL Chapter 8 test still on your plates. Get that done ASAP. Chapter 11, Mastery, I would plug away at that on a regular basis. Same thing with the required OWL problems. Plug away at those at a regular basis. And then bring those questions, if you have any, to for the Flex Chats. And then Chapter 11 exam, I'll release that early next week. That's going to be one where, again, you need to get 75% on the required OWL in order to be allowed to take the test, and then you will have the test have multiple shots at it. Now, revolving around the test, I said this in the last video, I'll say this again. Please take the test to its completion before asking any questions. It is a test. It is a test. It is a test. It is not a homework assignment. So I want you to test to see what you know. So try it. Not what you can ask questions about. Try the test. If after taking it one or two times, you're like, there's a concept on question number 3 that I really don't know how to do it, I can answer questions and respond to how you can do that style of question. But I'm not going to tell you what you did wrong exactly. I'm not going to tell you how to fix it so it's all better, especially if you've never even attempted the problem. You just look at the problem and say, I don't know how to do it. How can you tell me to do this? Think in terms of, if you were taking this test in class, would it be fair for you to call me over to your desk while taking the test and say, can you explain to me how to do question number 3? It is a test, so please treat it like a test. Take it in its entirety at least once. You're given 5 opportunities with each exam. If you get really, really stuck and you can't figure out by doing what you need to on your own, going back to the mastery questions. Remember, the mastery questions are a lot like the test questions. Going back to the mastery questions, getting the help on those, doing your due diligence before asking any questions. So far, I haven't seen a whole lot of that. I hate to be negative, but that's the case. On that note, if you get anything out of these videos, please do me a favor. Hit the like button, subscribe if you haven't already, and hit that notification button, because one of the things that's happening here is, I'm not going to make things too weird. I'm going to mention it today during our flex time. My wife took a little challenge yesterday, whereas I had said something about not having, only having 72 subscribers to my YouTube channel. And she took it as a personal quest to get me more. And you guys in 3 years have gotten me 72. And I will tell you, in the last 24, she's gotten over 40 by just asking people to like and subscribe to our channel. So if you haven't already, do that. It'll also tell you when I upload videos so you know what to go to. Anyway, with that aside, let's talk about the content. So this is chapter 11. We've done 1 through 3. We're going to do 4 and 5 today. Now, warning. 4 and 5 have a lot of math to them. And what I've done in both the 4 and 5 is I've tried to highlight the equations that you need to be able to use by putting them in yellow boxes. So these are the equations you need to know about. You need to know how to use them. And you'll see that there are the ones that are going to be used in our examples. So section 4 is all about the models of reaction rates. I usually like to address what is called KMT, or kinetic molecular theory, in the beginning of this chapter. And I think I have to some degree, but there's 2 big camps of models that are used to try to explain why reactions go at the rates that they go. The first one is called the collision model. It's probably the more common model, and it's the simplest model in my opinion, except as you're going to see on the next slide when we try to math it up. But here's the logic. In order, and this is it right here, in order for a reaction to occur, the molecules have to collide. That's the collision model. Okay, two contingencies. One, they have to collide with the proper orientation, which means they're aligned properly. If I want to unlock a lock with a key, the key has to hit the keyhole. I can't just tap the key to the lock and boop, it opens up. I have to have the right orientation of key and lock keyhole to make that lock open. Orientation is important. The more keyholes, for lack of a better word, that are on a molecule, the more spots that they can collide with another reactant to make the reaction take place, the more higher the reaction rate is going to be, because there's more opportunities for a reaction to take place. Second, they have to hit with sufficient energy. If you remember if you look back and you look at the videos from last week, the very first one that I think I offered you guys was a cutesy little one talk, and one of the things they talked about is reaction rates and how to get a date to prom. And you're like, whoa, what was that all about? I didn't watch that video. I got to watch that one now. Well, maybe not. There might not be a prom. Probably not. Might be a prom during the summer. Who knows? Anyway, so the point is, there were these two people who were walking in the hall, and they were moving at a certain rate, and they were going to collide with one another. And a reaction would take place. They would bang into one another. The books were going to go flying. But that was not going to happen if they were just walking along gingerly and tap one another, and no big deal. They had to be running. And when they ran, they hit with such intense attraction that they bounced off one another, and their books went flying. A reaction took place. There needs to be sufficient energy. Well, let's math this up. Okay. That energy that is required is called the activation energy. That energy that's required, the minimum amount of energy to activate the reaction, is called the activation energy. It's how much force, how fast do the boy and girl have to be moving in order for them to hit with enough intensity that their books go flying. How fast do the molecules have to be going in order to have enough energy that when they hit, something takes place. Okay, so let's talk first about the collisions. Now, if you think in terms of concentration, this example shows the red ball bouncing around, and on the left-hand side hitting two blue molecules. And on the right-hand side, it's colliding with four. Why? There's more molecules in the space. So the more molecules are in the space, the more reactions are going to take place. The more molecules are in a space, the more collisions are going to take place. We saw in We saw in the PowerPoints last week that concentration does matter. You increase the concentration, you're going to increase the rate of the reaction. That's because you're going to increase the number of collisions. But orientation is correct, is necessary also. Look at this example. We're going to use this example a couple times over in this video. You have carbon monoxide on the left colliding with nitrogen dioxide on the right. If the carbon bangs into the nitrogen dioxide at the nitrogen, nothing happens. But looking at the bottom, if the carbon, for lack of a better word, bangs into the nitrogen dioxide at one of the oxygens, what's going to happen is it's going to grab that oxygen off of the nitrogen and create carbon dioxide, leaving the nitrogen with only one oxygen to be nitrogen monoxide. Okay, so the orientation does matter. So let's math this up. Here we go. So math alert. This is what the collision model's mathematical representation looks like. It says that the K value, that's that K that we have, that we calculated back on section 2, the rate law constant, is dependent on three factors: the P factor, the Z factor, and the F factor. Let's talk about what those three are. The P factor is the steric factor. Let me get the steric factor. It talks about the orientation. How big is the keyhole? how many keyholes are in the lock? How many spots on the molecule could be collided with in order to form a reaction? How big are the spots on the molecule that could form the reaction? So that's all about orientation. And there's not much you can do about that. It's just whether or not the molecules have big or not. The Z is called the collision frequency. It gives the number of collisions per unit time at a unit concentration of reactants. How often per unit concentration, how often do the molecules collide with one another? Again, not very dependent just on anything other than numbers of molecules, but that's already built in there. How many collisions take place in a unit of time? It has a little bit to depend on how big the molecules are, how easy they are to bang into one another, and the like. And then the last one, the one we have some control over, and we're going to focus mostly on in this video, is the fraction of collisions, the F factor. The fraction of the collisions in which the energy of the colliding molecules is equal to or greater than the activation energy. How many molecules hit with enough intensity to cause a reaction to take place? What fraction, for lack of a better word, percent of the reactions result in a chemical reaction? What percent of the collisions result in a chemical reaction? So if P is greater, has a large steric factor, K is going to be big. If collision frequency is large, then K is going to be big. And if the fraction of collisions that result in chemical reactions is large, say 90% of the times the molecules collide, something's going to happen. Well, obviously, that's going to happen a lot more frequently. It's going to have a much faster reaction rate than one that only has 2%. Okay, that means 98% of the times nothing happens. Let's break that down. What's up with that F? Okay, we talked in the last video about logarithms. The F factor is a logarithmic relationship to two things. One, the activation energy, and two, the temperature. Now, this shows that the F factor is E raised to the negative activation energy over RT. Now that's important. Let's think about it. As I increase the activation energy, then my E to the negative number is going to get smaller. Let me find another way to express that. Let me see if I can get my pen to come up. There we go. So E to the negative 2 power is greater than E to negative 4 power. That makes sense? As I increase the number, the EA over RT, I'm actually going to be decreasing the E to the negative whatever that power is. So as I increase the activation energy, I'm going to make my F factor smaller. Vice versa, when I increase the temperature, I'm going to make my EA over RT smaller, which means I'm going to actually make my F factor bigger. Translation: the smaller the EA value, the larger the rate law constant. And the larger the T value, the larger the rate law constant. Well, that kind of makes sense from a conceptual standpoint. Let's step away from the math for a second. The lower the activation energy, the less energy that's needed in order for a reaction to take place, more molecules are going to have that energy. Think about that. The less energy that's required to make a reaction take place, the less energy that requires a reaction to take place, the more molecules are going to have that energy. Okay, you talk about go back to those two people walking in the halls, and those two people walking in the halls. If the young lady was walking with her books, and they were just hanging barely off of her, she was barely hanging onto them. There's just too much. There's a lot of papers saying it would not take a whole lot of energy to jostle her enough to make the reaction take place, and boom, books go flying. However, if she's got those books held on tight, they're wrapped with a bungee or a rope or something, and they're stuffed into a book bag, and the book bag is securely attached to her back, you're going to have to hit her really, 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 really hard in order for the reaction to take place. That means that the lower the activation energy, the more likely the reaction is going to take place. That makes sense. This Ignore the math. Second thing is, the larger the t value, the larger the rate constant. Again, that should make sense. The faster the molecules are moving, remember, T is directly connected to kinetic energy. So the faster the boy is moving in the hall, the more likely the reaction is going to take place. The faster the person is running and slams into the person, more likely they are to make their books go a-flying. So decrease activation energy increases K, increase the temperature increases K. Now the other model that's associated, that's collision model. The other model is called the transition state model. And transition state model is very, very similar to the collision model. We're going to address a lot less of the math, but we're going to focus a lot more on what happens when those molecules collide. And what the transition model states is when the reaction takes place, for a brief, very, very brief, fleeting moment in time, there is this other entity. There is this what's called the activated complex that exists where it's not reactants anymore, it's not products, it's something in between. Let's go back to that video that I keep talking about. And if you haven't watched that video, go back and look at it. It's cute and kind of helps with explaining some of the collision theory concepts. But let's talk about that boy running in the halls and the girl running in the halls, and they hit. And when they hit, did they hit with enough energy in order for the books to go flying? Well, one thing is 100% true. For a brief blip of time, those four things, the boy, the girl, and their two sets of books are all glommed together in one piece. And then the question is, did they hit with enough intensity for something to happen? But in order for them to react, collide, they actually have to come in contact with one another. That entity that exists while they're all together is called the activated complex. Now, the transition state model is a little more accurate than the collision model because very, very often, if you just look at bond enthalpies, the amount of energy that's in the bonds, broken into bonds formed, and do the math there, and again, come to AP, we'll talk a lot more about how to do that. But if you look at just the bonds that are broken, just the bonds that are formed, and what all that means, and how that relates to the amount of energy that's going to release, there's extra energy there. That extra energy is the energy that's in the creation and the breaking of the bonds in the activated complex. So it's going to be a little more precise to worry about that activated complex as it exists. Here's another visual. So suppose A and B collide, and A and B collide perfectly in a line so that the A hits B and B hits the A. They hit right in the middle, and if they hit with enough energy, they're going to split right down the middle, whoop, and when they split down the middle, they're going to become an AB and an AB. That's going to be an effective collision. Whereas if the B clips the AA, the BB clips the AA, then nothing's going to happen. They're just going to go back to doing the normal thing. They hit with not the right orientation and without enough energy. Both things have to take place for the reaction to take place. This reaction would not take place. Now, from an energy standpoint, and going back to the last unit where we're talking about energy, the energy or enthalpy of the reactants in the case of the reaction we showed earlier, the nitrogen dioxide reacting with carbon monoxide, the reactants are going to have more enthalpy than the product. So this reaction is going to be exothermic. However, in order for it to be exothermic, it has to, you have to put in enough energy to make it so that it becomes this very, very highly unstable activated complex that we have here at the bottom, this thing that has everything all together. That is your activated complex. You'll notice that the O and the C touch one another. They're stuck. That's really unstable, has a high amount of energy. Did I add enough energy? If I added enough energy, if they hit with enough energy that the molecules collided with enough energy, more than 134 kilojoules of energy, then the reaction is going to take place and they're going to go over the products. But if they hit with a less than 134 kilojoules of energy, then they're not going to react. And here's some examples to show you that if we were to do the experimental part and calculate the Ks of what happened, and we were to think purely on the transition state model and its math and the collision state model and its math and did everything there, you can see definitely the transition state model is a little more accurate. Just a little bit, but not perfect. But it's a little more accurate. Okay, so let's dive into the real mathy one, the mathy part of this PowerPoint, and that is, how does temperature relate to the reaction rate? Well, looking at what we just did, and talking a little bit about temperature, we should know, or you should know, that as you increase the temperature, the reaction is going to increase. It just makes sense. No matter whether you use collision theory or whether you use transition state model, the faster the molecules are moving, either the more often they're going to collide or with the more energy they're going to collide, but it goes back to the same thing. You're going to have an increase in reaction rate. So what we want to do is try to quantify that. So with reaction rates and temperature, you're going to have an increase in temperature is going to result in an increase in reaction rate. That should make sense because as you have higher temperatures, you're going to have higher kinetic energies. Higher temperatures are from higher kinetic energies. They're connected together. And the higher the kinetic energy, that means is there's a larger number of the molecules that have enough energy to surpass the activation energy of the reaction. So you actually increase the fraction of molecules that have effective collisions. I don't know whether you've ever done this. My kids did growing up, whereas if we would go to an event where they would get a glow stick or a glow bracelet or a glow necklace, we'd stick them in the freezer. Why? Because when you stick stuff in the freezer, it slows down the reaction. Temperature matters. That thing is going to die faster if it's in a warm environment. So if you want to try to save the glow stick for another day of going out and playing in the nighttime, maybe stick it in the freezer. Maybe when you take it out, it will actually still have some glow to it. Didn't always work really, really well, but it at least did to some degree. That's because if you look at this graph, this is that Boltzmann distribution, where they talk about the fact that as you increase the temperature, you have more molecules. The average kinetic energy is higher. The root mean square speed is higher, but also you'll notice that if you look at the red space underneath the curve, that's the number of molecules that have a activation energy that is greater than the activation energy, and it's an amount. That's cool. But when you increase the temperature by a little bit, you'll notice that green section is the additional number of molecules that have a greater energy than the activation energy. So as you increase the temperature, you're going to have a higher fraction of the molecules that are going to be have enough energy to surpass the activation energy. Okay, let's math this up. So if we look at the equation we had earlier on, where P times Z times the F factor, which I put here as the E negative EA over RT, steric factor doesn't matter with temperature. Making it go faster doesn't make the hole bigger, doesn't make the keyhole bigger. Collision number. Now, collision number is insensitive to temperature because, remember, the collision factor was more related to the size of the molecules and how big the molecules were and how often they would hit one another relative to the concentration and relative to the temperature. So the temperature is only going to drive the F factor, which is in this equation is the E to the negative EA over RT. So if I take this equation and I simplify it, and I simplify it by simply making my P times Z equal a constant, we'll call it A. Why chemists call it A, I don't know. I guess it's because it's the Arrhenius equation. That's my best guess. And I do my whole logarithm craziness with this. Now, logarithms, if you haven't taken if you haven't taken Algebra 2, I apologize. This may seem a little weird, but when you take the logarithm of this equation, you get this. Now, simplification, okay? When you take the logarithm of a number, ln k is ln k. Oops, I got my math. There it is. Ln k. Take the natural log of k as ln k. When you take something and multiply it together like you do here, a times e to negative e over r, In math, in algebra, in logarithms, when you multiply together, you take the logarithm of something that's multiplied together, it's actually the logarithms get added. So the a becomes natural log of a. And then since we're getting rid of the e with the logarithm, because natural log of anything e to the x, is x. Sorry, I'm writing on my screen and my screen is bouncing. There we go. Natural logarithm e to the x is x. That means I just pull out that negative e over r, and that becomes that part. So this is an expression that relates my k value to my three things. One, my activation energy. Two, my temperature, but also this a, which is temperature independent, and we're not going to worry about in this case at all. So expresses how the temperature is dependent. There's a temperature dependence on the rate. So as I increase the temperature, I'm going to decrease the amount that is being subtracted from natural log of a, because temperature is in the denominator, which is going to make my k value larger. However, and again, this is something that's a little disappointing to me because I really like the lab that goes with this particular unit, and we were not able to do this lab because of coronavirus craziness. But if I were to do this lab, one of the things that came out of this particular lab was we were going to graph, and if you guys watch, and I should say this as a side note, if you guys go back to the videos that I shared with this week, I put one video in there that was very, very similar to the lab that we would have done. And what they did was they ran a test during specific concentrations and then saw what happened to the rate to get the rate law, but then they did the reaction at different temperatures. This would be a graph of different temperatures, okay? And if I were to calculate my K value at different temperatures and graph the following, if I were to graph, let me get rid of this thing at the bottom. Guess it's not going to cooperate with me, is it? There we go. If I want to graph my K values that I got and my temperatures, I'm going to get a weird graph. But what you would have noticed if we had done the lab is if you were to graph the natural log of the K values versus the inverse of the temperatures, Kelvin temperatures, then you would have gotten a straight line. And what's kind of cool about this is this equation down here, which these two are the same. These two equations are the same. They're just written differently. I took this negative EA over RT and put it in the front. Okay. So, and then I pulled out the 1 over T because this is in the Y equals MX plus B format. Whereas the slope is going to be negative EA over R. My slope that I get from that graph would have given you the opportunity to calculate the activation energy of that lab. Works really, really well too. You guys all would have gotten very, very close answers, blah, blah, blah. I'm not going to fret over the fact that didn't happen, but it did. Okay. So anyway, what this shows is there's a mathematical relationship between the inverse temperature and the natural log of the K values. So what happens when you change the temperature? Well, when you change the temperature, you change the K values. Let's write an equation. Let's try to develop an equation. Let's try to derive an equation that allows us to relate Ks and temperatures. And we'll do it at 2 points. So the first thing we do is we write that expression that we just had on the previous page with 2 different Ks and 2 different temperatures. Now, activation energy does not change. A does not change with temperature, so those are the same on both sides. So if I take these 2 equations that I just wrote, one for situation temperature number 1 and one for temperature number 2, and I subtract them from one another, what I get is ln K2 minus ln K1, that's here. And then the LNAs they're gonna cancel one another because one's going to be subtracted from the other. And then what I'm going to get is negative EA over RT2 minus a negative EA over RT1. And what I'm going to do is I'm going to pull out my EAs over R's, and then I'm going to flip this to get rid of the negative sign. Originally with the negative sign out front, it was 2 minus 1. This is flipped just to put it in the order where there's no negative sign out front. So I have a relationship between my two temperatures and my two Ks. Another way to express that, again, subtraction is the same as division, is this way. And you're going to see this more in your textbook than any other way. And we're going to use it at least once in this example. But they both represent ways, the same exact equation, a representation that shows the relationship between temperature and the K values. Let's look at how we can use this. So in your book, there's a couple examples. And the first one looks at a reaction. There's a first order reaction of the decomposition of some substance A. So we're going to avoid them actually having identities and just say this is substance A. And things we know about it. First thing we know is as it goes from 15 degrees to 25 degrees, the rate doubles. Okay, rate doubles when we go from 15 to 25. Second thing we know is the rate constant at 40 degrees, not at 15, not at 25, at 40 degrees is 0.0125 inverse seconds. So let's see what kind of questions we can answer with that information. First question, S. Well, what's the activation energy? Well, we're going to have come with a game plan here. One of our equations that we've had so far has activation energy. We know that the K1, we know K2. Now, we don't know the actual Ks, but we do know that K2 is twice K1 between 15 and 25. And then we do know our R value and is asking me for my activation energy. So if I use this equation, like I said, we're going to use this equation sometimes, and this is one of those places we're going to use the equation here. And we put into this equation all the numbers. So we know 2, K1 is K2, K1 is K1. They're actually going to cancel. Okay? And then we have EA over R, and then we have our two temperatures. And really this just turns into doing some math. Take the natural log of 2, multiply it times 8.304, and then divide both sides by whatever the 1 over 288 minus 1 over 298 is, and we get that EA, the activation energy of this reaction, is 4.9 times 10 to the fourth joules per mole. So we have calculated the EA based on 2 Ks and 2 Ks and 2 temperatures. We have the EA over the activation energy. Second thing, what's the half-life? But wait, we have information at 15, information at 25, information at 40, but now they're asking for information, the half-life at 78 degrees. So I guess we need, since we know that our half-life equation for a first order reaction is dependent on the K, we need to know what K is. So we know our K at 40 degrees. We don't know our K at 78 degrees. And we just figured out what our activation energy is. So again, going back to the equation that we've used, we're going to take the 2 temperature, 2K equation, the Arrhenius equation, that now we have 2 temperatures and one of the Ks. We need to get the other K. Okay, and we also have the activation energy. And then we're going to use that K in the half-life equation to find out what the half-life is. So let's do this. So first thing we got to do is find out what K2 is. So we're going to go and plug the numbers in that we had into the equation. And then we're going to do the math and find that K is 0.0963. Okay? Then we're going to put that into the half-life equation. Natural log of 2 over K, plug that in, and we find that the half-life of our reaction is 7.2 seconds. Okay, last question. what temperature will the rate of the decomposition be 0.195? Will the rate of the composition of 0.165 molar be 0.124? So I want to know at what temperature the rate will be 0.124 if I have a concentration of. So what I have here is a rate law equation, which I have to find the K for, and then find out what temperature that K exists. So I have my activation energy from the beginning. I have my rate law constant at 40 degrees. I know what K1 is at 40 degrees. I know my rate that I want, and I know my concentration I want, and I know what my R value is, and I need to find out the T. So first thing I'm going to do is find out what the K is. I'm going to find out what K I'm looking for by plugging my concentration and my rate into my rate law equation, and then use the Arrhenius equation to find the new T. Because now, once I have the new K, I already have K1 and K2, I have EA, and I have T1, so then I have to calculate the new temperature, the temperature at which this new rate law constant exists. So let's show you how to do it. So first thing we do is figure out what K is. So I take my rate equation, I plug in my two numbers. Rate, which I wanted 0.124, is equal to K times the concentration, and I find my K is 0.742. Sorry, 752. Then I'm going to use my Arrhenius equation. Again, I have a K2. I just got that. I had a K1. I had a T1. I had activation energy. I have all those pieces. Then I had to go back and plug the numbers in. See what's missing. What's the only thing's missing is my T2. Then it's math world. Take my numbers, my natural log of 0.752 and my natural log of 0.0125. Do that math. Take this and do the math there. Put in my old temperature and then solve for K, or sorry, solve for T2, and I get 400 kelvins or 130 degrees Celsius. This reaction will go at that rate, at that concentration, at 130 degrees Celsius. Okay, so that's this use of the Arrhenius equation and a bunch of different ways to do this. So what's next? Next week we will be doing the last two sections of this chapter, and that is one's for catalysts and how catalysts change the rate of the reaction and why they change the rate of the reaction. And then the last one is mechanisms, and mechanisms are yet another way to be able to determine the rate law of equation. So like I said in the beginning, if you get a chance, please like, subscribe, and hit that notification button. I want to see whether you guys can help me beat my wife's 40 subscribers in a day. That would be fantastic. We've already broken 100 thanks to her. If you get anything out of these videos, please share as much as you can and let other people know. I know you guys are the only ones taking Chem 2 right now, but I'm hoping that these become something that can be used for a lot longer than that. Everybody be safe, be healthy, practice that social distancing. If you go outside, wear that mask, and I hope I get to see you somewhere at time in the near future. I miss you guys. Always remember, never forget, now even my Chem 1 kids know about it, sig figs really do matter. Take care. Toodles.